So I'm looking forward now to the next sessions. That's the technology behind AI that is shared by Fred Waltz. Fred Waltz is an AMD fellow. He's also a SIMPI fellow. He is a TC chair for Technology Committee 10E Essence, and he's also the chair of our AI task force. So he's deeply involved in everything AI, and Fred is right over here. So I hand it over to you, Fred, and enjoy.
So one of the things we talked about when we were planning this is sort of an opportunity to go a little bit more on the technical side in a technical deep dive. So I'm expecting a good presentation here. Dr. Zhenyu Gu leads the training at scale team at AMD. He has a strong experience in building high-performance AI ML infrastructure at scale that covers the end-to-end AI ML stack, especially with the rich experience of GPU clusters at scale. He has led several 100 billion plus parameter LLM pre-training, post-training, and inference serving projects. So, the industrial strength stuff that costs tens or hundreds of millions of dollars. So, Dr. Gu got his PhD from the EECS Department of Northwestern University. So please welcome Dr. Zhenyu Gu.
Hi, everyone. So very nice to be here and talk about AI and the key technology behind the AI from infrastructure to model. So for the audience, how many people are using ChatGPT daily? A fair amount. And how many people know that AMD has the GPU cluster that can train large model? Great. Yeah. Okay. We have a pretty good audience here today. Okay. So here, I think today we're talking about like a very large scale training. So for these are the top HPC cluster in US. We're talking about hundreds. I think it's 60 to 100,000 GPUs in the cluster, and you can see a bunch of those are built by AMD GPUs. The top two are both in AMD ecosystem. They are building by the most recent generation. One is building on the MI300, the other is on the MI250. And on the other side, we are also very care about the energy because today when we talk about all those big clusters, they're looking for electricity where you have very dense power, all over the place. And we are very green about that as well. It's very about data center. On the left, it's what looks like the basic components. You have the CPU, GPU, you have the memory, and you also have the communication as well. And in the middle, it's not just piling up. We are, organize it in a layer by layer way. From the bottom, we call it the leaf layer. To the middle, it's the spine layer, and then the core layer. So all the GPUs can talk to each other. So that's how we organize in the data center. So you see all those big building with a lot of racks and with GPUs. And even today, because it's generating a lot of heat, you are using liquid cooling as well. So it's getting a very complicated system. And each rack today, it's the equivalent weight is about 2 mid-sized car. So it's a very, very heavy, rack scale system that you put into the data center. And on the right, not only for the hardware, we are also looking to have the software. It's a very complex system with the scheduling, with the, optimization, how to run efficient. Those are very expensive GPUs. You want to get every bit of the GPU, right? And also, in addition, it's a huge system with tens, thousands of GPUs. It's very easy to get any of those GPU fail. And then you have to, restart the job. So that's a lot of stuff, to make the whole system working. So sometimes people say that great opportunity come from the great complexity. This is the case. And so behind that, you need the full stack of the software to support that. From the lower level, you have the operating system. And then you have one layer of the data center management, like the Kubernetes, to make, allocate all those GPUs when there's a job request coming, right? And on top of that, you have a lot of, monitoring, telemetry, a lot of things that monitor how healthy is the system. Are there any, failure nodes? Are there any, abnormal things happening in the networking? And then on top of that, that's the compiler, like the Windows system for our daily use. And then we have a lot of acceleration libraries, and then we run the model. Okay, and also with a very active, open source community, we're talking about PyTorch. That's the training framework. You write your model on the framework, and then you start to run. And also Triton, that's a kernel accession. You can write your own GPU kernel using this language and framework. And Hugging Face is basically a model hub. It gives you 1 million plus models. You have vision model doing doing all those vision understanding, and then you have the language model. You have the also the other type of model, acoustic model as well. Yeah. And then there are a lot of, ecosystem software that helping to, connecting all the dots and making the whole, end-to-end application. Yeah, I think we can get some very interesting, to my opinion, very interesting and very challenge problem from language model. That's what people are daily use today. And then to the weather forecast, we can do weather forecast using AI model as well. Yeah, it's also a multimodality model because we get different type of data and then to understand and to predict the future weather. And also for AI for science, you can do a lot of things like the doing for all those new materials, how to do simulation-based, experiments without using a lot of real material to understand the, the lower level structure of the new material. Okay. Yeah, the first thing is that we have the language model. Language model, it's transformer-based. Yeah, it's basically you can see we have the attention, which when you have a lot of, when the language come in, and then it's translated into token. Token is what machine can understand. And then it passes through the attention part. Attention mainly is telling you what's the relationship between different tokens. And then it's the MLP layer. MLP layer is more like the knowledge where store those knowledge. So typically for GPT size the model, today it's about trillion parameters. Okay. And it can store the word knowledge, all the internet based knowledge contents they can store in those models. Yeah. So it's a huge model. Definitely you cannot put into any single GPU, single machine. You need put into 1,000, even 10,000 machines. How can we do that efficiently? Definitely not only by human being to do manual design. We need a set of software to do that, right? And then you need to do a lot of, resource allocation, to chop all those models into different, compute units. And then you expand a lot of communication between different GPUs. So how to sort out those things, just like in the traffic hour, how can we have a better understanding of where come from the traffic and how we can reroute certain, traffic and make the whole system more efficient. So here we're talking about different type of the parallelism. It's like the tensor parallelism, pipeline parallelism, and the data parallelism. So this system can eat, trillion of tokens in couple months, and then it can understand and memorize all the data you feed in. So that's how the system works. Yeah. And also in order to further, improve the efficiency, we're also supporting the mixed precision training. What mixed precision means that in the typical GPU where we use 32-bit to represent a floating point. But today we're talking about using 8-bit, even 4-bit to represent one, meaningful token and go from there. Yeah. And also, as I mentioned, meanwhile, we also need to identify all those failures, and along those, training process, we may need to, remove one node or two nodes because they're bad, and then still running the job. So there's some elastic, resource allocation coming as well. Yeah. Okay. So those figure, it's a very beautiful figure that's showing that when we scale out, training on even larger number of GPUs, you still get fair amount of efficiency, like linear scaling. That's what typical, people are looking for, because that means you have a very efficient system. You can scale as much as possible, but to some extent, right? And on the right side, it's also telling how good your model is, right? Are you be able to, train it on a large scale? Are you be able to consume more data? On the right side, it's also telling you that's the strong skill people, typically talking about, is that, yes, we can eat a lot of data and on a large scale system, because there are a very challenging problem when you have 10,000 or even 100,000 GPU with the same speed to pipeline the token, streaming the token to the model. Sometimes they cannot learn that quick or fast. They need some time. So in that case, that's why we need to design a more efficient model to consume those data. Okay, next case is about the weather forecasting. So for our orbit, it's a lot of data. You have the ocean data, you have the thermal data, you have the, humidity and other type of data. Sometimes it's the picture, sometimes it's the video, sometimes it's the 3D text-based data. So how can we combine all those data together and let the model to learn, and then get the real weather forecast? So here we adding couple layer of the we call it the translation layer, that they can convert all those different type of data into text-based or token-based data, and then in the middle somehow the model can figure out more like you have different type of language, and then they can combine them together, like they can translation and unify into one type of data, and then start to understanding what's going on there. Yeah. So here, one of the big question is that how can we consume such huge amount of data, right? It's and also different type of data. So here we're also doing different way to partition the data. And then we know there are some sparsity in the data. So you may not have all the data have relation with each other. So you don't have to put them together at the same time to learn. You always can do, by sparsity means that you can do a divide conquer based learning methodology. Yeah, so those are the different things that we see, especially for this one. We do a special parallelism. Basically, we understand how those data correlate with each other. Then we can split them and then do a hierarchy based learning. Yeah. Okay, so we hybrid sharded model, and then 113 billion model parameters, and I think it's about 1/3 of the GPT-3. That's like 2 years ago. Yeah. And it's the largest, by that time, it's the largest vision transformer model, which means the model can understand the image and then produce the results. Yeah. And then up to 1.6x flop. to support this learning, it's running on almost 50,000 GPUs together at the same time for a couple months. Yeah, that's what we, to train this model. And then 90 to 95% accuracy for short-term weather forecast. That's the results. And also 60 to 80% long-term accuracy. This is also very efficient, in terms of in the prediction time. When we do the training, we just teach the model to learn how to predict. And when you predict, you just need a couple of GPU to deploy it. So, and at that time, at that time, you can see that's very energy efficient. You only need a couple of GPU or maybe 10 GPUs. You can start to predict and telling you what's the weather forecast and for hour base. So that's how the technology helps today. Yeah. And then the third one, it's about AI for science. So people are trying to use a model to learn or predict the new, structural underneath the new material, right? So here we use a graph. So graph, by that means it can, condense a lot of feature for each, components, and then different feature represent different things. And then, so here we need a multi-headed graph, and it's a convolution neural networks. That's the key behind the vision model or deep learning model. And all those optimization is done on the graph. And here we have a lot of things need to learn at the same time, because for a material, you are talking about how hard they are, how heavy they are, and other couple, things that happening along this time, right? So it's a multitask learning at the same time. So what we do is that then there's question how many tasks you need to learn in order to explore, and can we doing that in a more efficient way? Yes, we can. So here we did a HPO, which is a hyperparameter optimizer. So using optimizer to determine what are the top K, most accurate and energy efficient, the graph neural network we need to pick up to do this analysis, right? We cannot do all the combination. It's too many and too time wasting. But we know what's are the most similar structure that we can do this. So that's why we do the top K. Top K means the most similar structure or most relevant information you need for this training. And then we run this to make sure we have all the aspect of those materials. So we run the ensemble version. Ensemble version means that we combine all different top K graph, and then we have a neural network to learn the relationship between those different type of, the neural graph, and then decided whether it's a good or bad combination. Okay. And then this is also running on 8,500 nodes, and each node has 8 GPU. So it's 8 times 8. It's 64,000 total GPUs to run this. And then I think this is also very critical, because you find a more efficient way to run the neural graph understanding and then to do the further prediction. So therefore you have a fast turnaround time. And the key technique behind this is that we need a large system, parallel system to run this. And then it's a multitask learning. So how to find a smart way to do this combination, right? And also scalable and other effect. But the impact is very big. So it helps us to accelerate the discovery of the novel material. And also the all those experiments results doing by the neural network prediction showing a very high fidelity, because we are doing a lot of tasks a lot of aspect of the new material at the same time. So all those help us to find the right path to do this discovery and exploration. Okay. So one more step. I think that when we scale out more and more, think about today, you are talking about 10,000 GPU, 100,000 GPU, this level, and even gonna be bigger because people do believe the parameter size is related to how smart the model is. So I do believe we're gonna to scale even further. And from all the news from OpenAI, they asking a lot of chip company to work with them together, right, and deliver huge, data center. I think that's on the right path. And because of this faster scaling, we're having a lot of issue with, communication, because those are the slowest part of the current EAT system. And what we do here is we find there's some way that we can overlap and our, the computation and the communication. And that said, as there are two different, major components that we can do in a pipeline way. This is talking about how we can further, to explore in this space. Yeah, there are different ways to do that. The main issue is that when you scale out to more and more GPU, you have more communication going on across the network within the data center. So you want to find some way to reduce the communication time. Therefore, they spend more time on the computation, let the GPU busy. Yeah, there are certain fusions that we are doing, exploring at this time that we are trying to make it more efficient and therefore getting more, performance gain from the GPU cluster. So I think the single, summary here is today, AI is still scaling at a very fast pace. But I think only scaling won't help, won't make that happen because you will hit your ceiling sometime, right? And there are physics, limitation ahead of us. So not only to do the big scaling, of course we need the scaling, but we need to scale more efficient and also scale across different domain like the science, like the energy, language, planet, also the media, right? Multimedia, industrial as well. So there are a lot of things ongoing, and I do believe that we need a domain-specific way to do software, hardware, co-design, and to achieve the best efficiency for different scenario. So that's why for AMD that we provide a end-to-end solution that cover both the efficiency and the stability of the whole training system. That today it's covered the end-to-end model, development cycle, and also align with our data center telemetry and the scheduling system and other things together. Yeah, I think that's how we can, manage a 100,000 GPU cluster. Yeah, I think those are all the slides for this session. Yeah, thank you.
Okay, thank you very much. I think we have time for a few questions, if there are any from the audience. Okay, can you, yeah.
Oh, cool. Thank you. I have a question about the HPO, the optimization. You mentioned selecting a primary or best method. Does that method vary based on the underlying infrastructure if you run the same HPO on a different supercompute cluster?
Yeah, that's a good question. Actually, it depends on the underlying infrastructure, because sometimes when they build up the underlying infrastructure, they may use different bandwidth to connect all those GPUs, right? Or they may use different number of the switches to connect the GPUs. Those are affecting your underneath, ability to talk to each other, because today it's not only single GPU, single node, it's about the whole system. So that's one thing. The other thing is the storage, right? You still have to have a lot of storage in the cluster because they are very fast. They need a lot of data to feed. So that's also another parts, right? So consider all those parts, then you can talk about what's your optimization, what's your strategy to fully utilize all those GPUs. So what I see is that today we're moving from CPU centric to GPU centric because they give you more compute power. And then every software piece, every hardware, they're just, to around those GPUs, making them, running 24/7 without any waiting or stopping, right? Because they're waiting for data to feed them. Yeah.
Hi, thank you. Nice presentation, very impressive work. I guess for me, the elephant in the room is, what about media and entertainment? How do you see some of this technology being applied to the problems we're dealing with?
Yeah, great question. I think there are a lot of examples. I don't know how many people start to play Sora 2. Now it's, released by OpenAI. You can make your own, video or short video, like TikTok style short video, just by typing some, a text message to let the model to generate with some of your, personal, picture or a quick shot of yourself, then you can start to generate those. I think it's will affect the media a lot, because think about that. Today, the model can think in minutes, and then later on they can think in hour or even in longer time. They just need enough, time to compute, right? In that case, you can do a lot of things by yourself, as long as you can interact with the model in a more, efficient way, and then they can start to iterate what you want to implement into a video or image or even other type of way, even the speech, the voice as well. What's the rule of?
The role of SMPTE standards. So this group is SMPTE. So what is the role of SMPTE in developing standards for training?
Oh, okay. I think there are still a lot of things like I think it's for reliability, because model is not stable at today. They may give you something not that high quality. I think those are like one of the things that you guys can think about and discuss what's traditional measurements on all those quality and the things on the media industry. And today, something still apply. I think there are still other things that need to ongoing monitoring all those, because now today everyone can make their own, studio with a capable model. They can start to produce. So a lot of things need to, updating today. Yeah.
Hello, thank you. You had mentioned that OpenAI had made deals with multiple processor vendors. And I note that those processors have very different architectures. I'm curious as to whether this is a parallel path trying to do the same thing with different devices, or are these devices being focused on particular subsets of the overall architecture? Communication versus.
Yeah, I cannot answer the question represent OpenAI, but from my point of view, they have their own type of workload. They know what's the percentile of different workload, and different workload, when it's running in scale, they want to have more efficient hardware to serve that type of workloads. That's my basic understanding. So I think all the chip designer are going to provide very high power efficient processor, general processor for them to compute, right? That's the basic for it's just whether, for example, one example is, do you need a mansion or a condo or apartment or just a single family house? It really depends on your scenario, your different, consideration. That's my analogy to your question. Yeah.
We'll make this the last question for this part.
Thank you. I was curious to know if moving from LLMs to 3D Gaussian splats, if there's going to be a significant change in the architecture for compute, storage, and networking, and if that should be standardized through SMT.
Yeah, I think language model, they are text-based. So I think they are most less on the bandwidth requirement, on the storage requirement. But once it's to the diffusion-based model for video, for image generation, your training data gonna be also video clips or image files, right? And on different resolution. And I think for that point of view, it will give you another higher requirement on the bandwidth requirement, on the storage, on the data streaming to the compute, because it's more, more requirement on those type of workload. Yeah.